Water can act as an acid or a base. It is amphoteric. We can imagine it reacting with itself. If one of them acts as an acid and the other one acts as a base, right? We could imagine one of them donating a proton to the other. So what would the two products be if that happened? Hydronium and hydroxide. Okay. And that actually happens. If we had a pure sample of water, it would not be just water molecules. We would occasionally, and it's a very small amount, but we would occasionally have a case where a water molecule would donate a proton to another water molecule. Okay?
Spontaneous dipole moment.
Absolutely. Well, yeah, you could think of it like that. Even deionized water, while we said it's a non-conductor, it will have a tiny amount of ions in it. Usually that's not enough to be conducting. It's not enough to make a light bulb light up, but it actually is measurable. Okay? So the equilibrium constant for this equilibrium up here would be concentrations of hydronium and hydroxide on the top of the fraction, right? And what on the bottom of the fraction? It's just liquids over there. So this equilibrium, it's called Kw now for the autoionization of water. It's called the ion product constant of water. It's just the concentration of hydronium times hydroxide. Okay. For water's autoionization, it is a constant. It is 1.0 times 10 to the minus 14. Does that number 14 look familiar to you at all? The reason the pH scale goes from 0 to 14 comes from water's autoionization. It is sort of a coincidence that it's just a round number like that, okay? But it happens to be useful to us that it goes that way. So that's why the pH scale goes from 0 to 14. We'll talk about that, but it comes from this number. There's nothing magical about that, though. That's just the equilibrium. That's when the rate of ionization and then deionization is equal. Okay? It is temperature dependent because there's energy change associated with it. Okay? So at 25 C, so that means pH calculations are temperature dependent. You'll always do them just at room temperature unless you're told otherwise, and correcting for temperature is sort of difficult, but that sometimes has to be taken into account if you're doing very precise physiological pH readings, because that's at 37 C instead of 25 C. All right. So these two in pure water will be the same, because if all we have is water molecules, then for every one that lost a proton, we have to have one that gained a proton, okay, in pure water molecules. So they're going to be the same, and if this is the formula, how would we figure out what their individual concentrations would be? If it's that one times that one.
Constant and divide by one of the concentrations?
Divide by 1. But if those two are the same, if those were x, if it was x times x equals that, it would be x squared equals this. So we'd have to take the square root. Okay? It's going to be the square root of 1.0 times 10 to the minus 14. Okay? How do you take the square root of a power of 10? You guys know that?
You divide the power by 10.
Yeah. What is the square root the same as a power of? 1/2. Okay. So it's here 1.0 10 to the minus 4. Here, I'm going to write it out. Okay. To the 1/2 power. So you multiply exponents, right? So it's 1.0 times 10 to the negative 7. Okay. So in a pure water, in a sample of pure water, just water molecules, we'll have 1 times 10 to the negative 7 molar of hydronium and 1 times 10 to the negative 7 molar of hydroxide. Okay? And it has to be that because they get multiplied together to make 1 times 10 to the minus 14 total. Okay? So when hydronium is equal to hydroxide, when we don't have an excess of either one of those, what would we call that kind of solution? It's not acidic, it's not basic, it's neutral. Okay? So a neutral solution will have those concentrations of both hydronium and hydroxide. I think you guys see where this calculation might be going. What is neutral pH? Okay. Now, in a solution that's not pure water, in a solution where we've added an acid or a base, that will form excess hydronium ions or excess hydroxide ions. Okay? But because of this equilibrium that happens, no matter how much of one of those we add, the equilibrium is going to establish itself so that their product is equal to 10 to the minus 14. Okay? It's kind of like Le Chatelier's principle, the reformation of an equilibrium. Okay? So if we know one of those concentrations, we can figure out the other using that formula. Because hydronium times hydroxide is 1.0 times 10 to the negative 14. Right, that's Kw. If I want to know the hydroxide ion concentration, we have to do Kw divided by the other one, right? 1.0 10 to the minus 14. If our hydronium is 2.5 10 to the minus 3, I get 4.0 10 to the minus 12 molar hydroxide. Okay? So because of this relationship right here, because this equilibrium will always reestablish itself, that means any acid we add will lower the hydroxide concentration, okay? And vice versa. Any hydroxide we add will lower the hydronium concentration. The only time they're equal is when the solution is neutral at 10 to the minus 7 each for both of them. Okay? So if hydronium is greater than hydroxide, the solution is what?
Hydronium is greater.
Yeah, this is the source of acidic properties, right? Okay, that's an acidic solution. Other way around is a basic solution, and when they're equal, the solution is neutral. Okay? So it's because of this autoionization equilibrium that those two are like a seesaw with each other. If we've added a whole lot of, you can think of it like Le Chatelier's principle. If we add a whole lot of acid, we're gonna use up some of the hydroxide. Okay, so that's going to go down in order to reestablish our equilibrium again. Okay, and vice versa. We'll talk more about that when we do buffers later on. Okay, so now we can finally talk about the pH scale. We could just talk about, there's nothing stopping us from just talking about concentration of hydronium ion in solution. Okay, that would be fully effective, but the pH scale is used because it's just a regular positive number, usually between 0 and 14. just because it's just because it's easier to say 7.5 than 1.0 times 10 to the negative whatever, you know. So it is a negative logarithm. Okay, that's what turns the power of 10. Okay, we have a range of powers of 10 from approaching 10 to the 0, that's 1, all the way to 10 to the negative whatever, you know, 5, 10, 15, whatever. Okay, that translates those negative powers of 10 into just positive numbers. Okay, the reason it's a logarithm is because it's taking an exponent and turning it into a number, and it's a negative logarithm because those are negative powers of 10. Okay, so this will be a quick thing for us to do before we go. Let's do pH calculations with no calculator. You can do it if it is an exact power of 10. Okay, that will help you sort of understand what that logarithm does. If we have a solution with hydronium ion concentration, H3O plus in brackets, if it's 10 to the negative 2 molar, okay, pH negative log, okay, so for this one, negative log of, okay, so all those minus signs there, that's just sort of off to the side here. Let's remember what a log does. What would be the log of 10 to the minus 2? A regular common base 10 logarithm says, to what power have I raised 10? What is the exponent to 10 here? Okay? So, to what power have I raised my 10 here? Have I raised it to the 2 power? No. I've raised it to the negative 2 power. Okay? So, but pH is negative logarithm. So the negative logarithm would just be sign switched from that. Okay, so that's what pH does. It takes a 10 to the negative 2. If it's an exact power of 10, it becomes an exact pH. So exactly 10 to the negative 2 means exactly 2 in the pH scale. Okay, so it's essentially the negative exponent just turned into a positive number for exponents. Okay, what would pH be for 10 to the negative 3 molar? Yep, pH negative log 10 to the minus 3, which is 3. Okay. Now, I think you guys know which way the pH scale goes. So which of those is more acidic? 2. Yeah. Okay. But now look at these concentrations. 10 to the minus 2 or 10 to the minus 3. Which of those is more hydronium? If we write out those numbers, right, 10 to the minus 2 is 0.001. Yep. 10 to the minus 3 is 0.001 molar. Okay. Yeah, that works. So, of these two, this is the more acidic. This is the less acidic. Right? You can look at those concentrations to see how that goes. But that's why the pH scale gets more acidic going down towards 0. Okay? Because as the negative exponent is approaching 1, okay, that's becoming more acidic, but that sign change makes our positive number approaching 0, essentially. Okay. So I think we're out of time. We'll do pH calculations for strong and weak everything next time. This gets us ready to go.